So last time we saw again that we had a matrix whose entries were Brownian motions, independent Brownian motions, W11, W and N, say Nn of t. So we had an n by n matrix, random, okay, whose entries were random functions of t, whose distribution was the Wiener measure, so they are called Brownian motions. And we had built a random orthogonal matrix that diagonalizes this one, and we have seen that the values, the eigenvalues of the diagonalized matrix, they satisfied this sort of singular mean field equation that we already have written many times. Lambda I dot is the sum, is 1 over n. N is the size of the matrix. The sum from 1 to n, j different from I, or 1 over lambda I minus lambda j plus some Brownian motion here, w dot I, with some initial condition which is actually not very important. Because any initial condition we can make an initial condition here diagonal by just diagonalizing the initial data, and this transformation would leave the distribution of this random matrix invariant. So, okay, some lambda I of times 0 where some lambda I 0. And we were thinking that we can certainly number the eigenvalues in such a way that lambda 1 is the largest one. We have proved that they are, or say discussed that they are, with probability 1, they are all distinct and they never touch. So since the the paths are continuous, since the lambda are continuous functions of t, we can uniquely identify, I don't know, the largest one as a continuous function of t, the second one as a continuous function of t, and so on with probability 1. Okay. And just then we wanted to check what happens when n, this number n, goes to infinity. Just it will be also useful to use today a simple fact that we discussed last time. So if mt, so it's a real value, it's a continuous, it's just a remark that will be useful today. If mt is a continuous martingale, with the expected value of e to the 1/2 and the quadratic variation of m at mt is finite, then the random number, the random process exponential of mt, this is an mt minus 1/2 its quadratic variation, is a martingale. Okay. So let's say remark 1, and let's write a remark 2 that we had also discussed either last time or two times ago. So if I consider a process of this type, but let's call x because it's sort of a generic process, equal to some vector, tangent vector f of x plus w dot. We had discussed that for each smooth function phi from, say, of t and x, okay, the random function of t, so the process, let's call it mt, equal to phi in t and the x of t minus phi of 0 and x of 0 minus the integral between 0 and t of this f. So the derivative in time of phi, partial derivative in s xs plus So this was just Ito formula, okay, plus f of xs scalar, the differential of phi in s xs, plus 1/2. It will be useful to write this formula where there is a constant in front of the Brownian motion, because here I forgot the constant 2/n. So if here there is a constant c, let's call it square root of c. Here I will have a c is positive, Laplacian of phi in s xs ds. So all this quantity, phi in txt minus phi in 0 x0 minus the integral of the generator of this process, which I wrote explicitly, is a martingale. Is a martingale. And at some point we had very quickly checked that its quadratic variation is just, so MNT is nothing but the integral of the gradient of phi squared in ds. Okay. So certainly phi is smooth with all the derivatives bounded. This expected value for this quadratic variation is without any doubt finite, because just the function is bounded by itself, the gradient of phi. And therefore we get that, so from these two previous remarks, we get that for this process and for all functions phi with, say, two bounded derivatives, the exponential of, okay, phi of t and xt minus phi of 0 x0 minus the integral in time. So let's write it as exp, to have a bit more exponential of phi of txt minus phi of 0 and x0 minus the integral between 0 and t of all these things, okay, ds phi plus f d phi plus c over 2, the Laplacian of phi minus 1/2 from here. The integral of, I forgot the constant here, the same constant which is here, sorry, so there is a c here. Constant gradient of phi squared, all this function computed in s xs. So the integral in 0t in ds of all this function, okay, it's just whatever was here minus 1/2 the quadratic variation, which is also an integral, is a martingale. So the exponential of all this, sorry for the bad blackboard management, let's call it e phi, okay, it's of t, is a martingale, okay, because we said if we have a continuous in time martingale such that the expected value of 1/2 of the exponential 1/2 the quadratic variation is finite, then this is a martingale, the exponential of nt minus 1/2 mnt. And for this specific process, like this one, for instance, we had seen that this is a martingale, mt, what I wrote here. And so if I do e exponential of mt, all these, minus 1/2, so c over 2 this integral, which I put it here, that's a martingale as well. In particular, what will be very important for us is that the expected value of e phi at time t, this doesn't depend on t because it's a martingale, so is equal to the expected value of e phi at time 0, which is just 1, because for t equals 0, this is just the exponential of 0. Phi of 0, 0 minus phi of 0 x0 minus the integral from 0 to 0. That's 0, and so we get 1. Very well. Why? Okay. And the last thing I want to recall is that we had defined already since the first lecture the spectral measure of our matrix, which is nothing but phi n. Phi, let's put the n upstairs, up, and here t is 1 over n, the sum from 1 to n of delta over lambda I of t. So we put the weight 1 over n at the position of the random of this random eigenvalue time t, and we are seeing pi n as a continuous curve. Let's fix the final time horizon, so let's say capital T, with values in the probability measures over R. Okay. So we're here, remember that continuous means that the map that associates to T the integral of a bounded continuous function f in d pi n is continuous. Is continuous. So for each fixed n, this is nothing but 1 over n, the sum of f of, so this is t in x, of lambda I of t. So since each lambda is continuous probability 1, that's certainly a continuous map. It's continuous for every bounded continuous f. I said it, but I didn't write it. And okay, so we already know from the very first or maybe second lecture that pi n of t converges for every t to sigma t, where sigma t was the semicircle law scaled with t. So sigma t of x is just absolutely continuous with respect to the Lebesgue measure with density 4t minus x squared divided by 2 pi t. Okay, restricted to the where the density means 0 when x is not less than 2 square root of t. Okay. So I would like to discuss two things today. The first is a bit sharper asymptotic for pi n. So the probability that, so to estimate the probability that pi n is not close to sigma t, but say is close to some other measure, or say some other continuous curve of measures. And then to use this result to estimate again the say more or less sharp behavior of the largest eigenvalue of the matrix. So in our notation lambda 1. Okay. So this is, and okay, we had checked that these eigenvalues never meet each other with probability 1, and we had some not very sharp quantitative estimate on what is the probability that they are closer than epsilon up to some time t, that are never closer than epsilon up to some time t. So the main problem, technically speaking, is that in the equations for the lambda I, we have a singularity. So we had made some more or less quantitative estimates for this, how to remove the singularity. For what I discussed today, the bound we had is not enough. Because we have fixed n, and how small we should take epsilon to have a large probability that any two eigenvalues are never closer than epsilon up to time t would depend on n. And since we are going to do the limit n to infinity, this dependence was sort of catastrophic. At the same time, in some sense, there is also an advantage in taking the limit n to infinity, and the advantage is that there is not really a problem if just two eigenvalues are close, because I mean just close less than a fixed epsilon, because then here you have a 1 over n. So in the sum. So like it's not that one necessarily needs a harder bound than what we proved 2 lectures ago. Is just a different bound. So it's 2 lectures ago, n was just fixed, and we used the quantitative bound to prove that this system was well posed. And today I will not do it, but we would rather need to control like this sum to control that in this sum the contribution from very close eigenvalues is negligible. So if two eigenvalues get very close, but in such a way that divided by n still has no large contribution, is not a big problem. So okay, as I said twice ago, we are thinking that 1 over x, or maybe the logarithm, is a smooth function, which of course is not. the exact bound that we used 2 times ago to replace this function with a smooth one wouldn't work today, but I still will pretend that this is a smooth function to avoid technicalities. Okay, this we should probably remember. Okay. So I think here we discussed a bit briefly what was the topology on P of R. So this was, remember, the weakest topology, such that the integrals of continuous bounded functions are continuous functions. So on pi of R, there is the weakest topology, such that the map that associates with probability mu. So let's write it. If I have a probability mu in P of R, the map that associates the integral of f in the mu is continuous for every continuous function, bounded function f, compactly supported, say, function f, if I want to declare it as a topology. So C0t in this space just means continuous functions with values in here, and it also comes with a topology. So two curves of probability measures, they are close, so like mu1 and mu2. So we could, yeah, let's do this. Maybe it takes some time, but it's good to write it. Okay. So if I have two probability measures, so R, if I take, say, the space of continuous compactly supported functions on R is separable. So take any countable family Fk, which is dense in Cc of R. And we can define here a distance, okay, a distance between two curves of probability measures, mu and nu, as the supremum of T. And here I just make a sum which is like a small if in some sense all or many say of the integrals of this function fk are small. So here I will do the integral of fk in d mu t minus the integral of fk in d nu t. Say absolute value multiplied minimum 1 to make sure that this is convergence series, and 2 to the minus k. Okay, so you see that the curve mu t and the curve nu t, they are close. Okay, if for each so if they are close for each function fk, and therefore since they are dense for each function, the integral of f in d mu and the integral of f in d nu are close. Okay, for every function, because if I know, say, if I know it for the first 10 function, the rest of the sum, so the first 10 are small and the rest of the sum is less than 2 to the minus n plus 1. So that's the idea of this distance. It's just one of the many distances you can put on this space, but just to get an idea who is the topology on this space C0t. So what I'd like to prove first, or to sketch the proof of the first theorem, is that for each mu in C of 0t in our space with values in P of R, okay. So let's write it in here. The probability that pi of n, let's write it first informally, then let's check what it means. It's close to mu, so in this topology. This goes as for n large as the exponential of minus n squared over 4. So in here there is a suitable norm that I'm going to define. So there is dt mu plus or minus. It should be a minus dx of mu times the convolution of mu. So let's give a name to the function 1 over x of the measure mu with the function phi okay, squared. And here there's a norm, let me call it h minus 1 mu. And okay, who is exactly this norm? I'm going to define actually during the proof somehow. But in some sense, you should think that when this is 0, mu t is necessarily the semicircle law scale at the time t. And so if mu is something else, just the probability of being close to mu is of the order e to the minus n square, sorry, it's root to the fourth, n square. And how much mu is not some quantitative version of how much mu is not the semicircle law. So what we're going to prove exactly is something a bit slightly different. So what does it mean? First, let me tell you what does it mean. This means that so if we take the logarithm of both sides, so the logarithm of the probability that pi n, okay, and close to mu means that pi n is in a ball in this topology around mu, okay, ball of radius delta around mu. So if you want that the distance between pi n and mu is less than delta, I take the log. So if I take the log, this should be minus n square. I want to take n to infinity, so I divide by n square. And I take the limit when n goes to infinity. So, of course, being close, I should then take the limit delta to 0. And this equals this number. So minus 1/4 dt mu minus dx mu star phi squared. So where this norm, I will define it exactly when we prove. So again, the probability that pi n is close to a given mu is closer than delta to a given mu. When I take n to infinity, it goes as e to the minus n square. This number, say, plus a correction that goes to 0 with delta. Okay. Let's prove just an inequality, less or equal. And to this aim, remember that lambda dot I was 1 over n, the sum of j from different from I wrote it 10 times already, plus the square root of 2 over n w dot. Okay, but this I can think it's just for each fixed n, this is just a diffusion process as we achieve. I mean, I can write it as lambda dot I equal to, as we wrote just exactly on this blackboard minutes ago, some f of all the so lambda dot is f of all the lambdas plus the square root of 2 over n, some n-dimensional Brownian motion. So, yes. Okay, so for each function phi from Rn smooth with all bounded derivatives, and actually to make the calculation rigorous, it would be good if we take this phi 0 in a neighborhood of lambda I equal to on a neighborhood of lambda I equal to lambda j for any of the I and j's. So for each smooth function phi from Rn to R, we have that this thing, if phi was a martingale, this was the exponential of what we wrote before. I'm gonna write it later, no problem. Martingale is a martingale. In particular, its expectation is 1. Let's say the final time t is equal to 1. Okay, so yes. So for each measurable set, let's call it A in our space, C0T with values in P of R. We have the probability that pi n is in A. Okay. This I can write it as the expected value of course, the indicator function of A. And I can just multiply. So this is a function of the curve lambda, if you want. I can multiply and divide by this exponent here, this martingale, which is positive because the exponential of something, and so I can multiply and divide by this martingale, and very well. And then, so I just want to take 1 over the martingale out of the expectation. How can I do this? Just taking so here I have just to take the less or equal than the supremum over all the lambda such that, so over all the curves lambda such that this martingale, such that pi n is in A of 1 over this martingale times the expected value of the martingale, the indicator function of pi n. Now, so here pi n is a function of our paths, and this martingale again is a function of all the lambdas. Okay, so of course 1 over the martingale inside this integral, inside the expectation, I can take it out with an inequality if I take the supremum over all the lambdas such that pi n is in A. Because if pi n is in A, this is pointwise bigger than 1 over E, the supremum, and if pi n is not in A, here there was 0, so I have no inequality to do. And now this factor here is less than 1. Because this is positive, Et is positive, and this is an indicator function is less than 1, and the expected value then if It was 1. So this is less than the expected value of the martingale, which is 1. Okay, and it's time to choose the function phi. So we have to choose a function phi. I wrote Rn, but we can also take it that depends on time. That's important. So it's a function from 0t times Rn. Sorry. But it's a smooth, so it's exactly the same writing. So phi, so I choose it in this way. I fix an arbitrary function smooth with bounded derivatives f from R from time and R with values in R. So f is a function of just one eigenvalue, if you want. And I take phi of all the lambdas as n begin times the sum from 1 to n of f of lambda j and t. Phi of t and lambda, f of t and lambda j. Okay. So given a measure mu in probability measure on R, let us denote the convolution. So this is also called the Stieltjes transform, actually. Mu star phi is nothing but the integral, so sorry, phi was like this, was just the function of 1 over x. Is the integral 1 over x minus y in the mu of y. Okay. So for us this will make sense. We will always compute it for measure, for this will make sense. Of course, for a generic mu, it may happen that this integral has no sense. But as we will see, we will be interested mostly in the case where x is out of the support of mu, so there is no problem to define this measure. But again, if you want, this is one of the cases where I'm pretending that 1 over x is a smooth function. And so let's compute who is the martingale for this choice of phi. So who is Et, or maybe capital T, phi, when phi has this form, n times the sum of a given arbitrary function f in T and lambda j. So f is a function of one eigenvalue, and in this way I make a function of the n eigenvalues. So this is nothing but the exponential of, so here I had to write, phi at t and lambda t. So there is an n, so I can write it as n. So this would be, for instance, n phi of t and lambda of t. So this is, n squared times 1 over n, the sum of f in t and lambda I of t. Okay. So let's denote f of this function as f with an index t, as we do also for pi n. So this is what? This is nothing but n squared pi n t integrating ft. Then there was, so that's what it is. Then we had in the martingale this. Just fine, n is here. Then we have minus n squared, the same phi times 0 lambda 0. So this is pi n times 0 of f0. And then there was the integral. So let's write it here. It's all in the exponential. Minus the integral between 0 and t. And here I had to put, dt phi. So here we will have dt phi. But dt phi is nothing but with the same type of computation. N squared pi n at time t. So dt phi at time t. Of the integrating the function dtf. So if I write it as an integral in dt, we will have, I will put here n squared, or let's put it here, n squared, ptn of dtf, very well, that's this term. Then we had similarly term which was the only nonlinear term. Here will be the term where there was, so all the function f of lambda d phi. Okay? So this what does it mean in our case? This means sum over all the I and j, so over all the j different from I, of 1 over lambda I minus lambda j. And this is the component I of f. And then I have to do scalar the component I of the differential of phi. So the component I of the differential of phi is just di phi. Let's write it here. So here, let's write it here. Di phi is the derivative of phi with respect to lambda I. So it's nothing but n times f prime of lambda I. Okay. So here I have to do also the sum over all the I of f prime of lambda I. So if I use this notation, you see that here I have, so there was a 1 over n coming from here. So here I can write this. It's not one sum of the I of some function lambda I. There is a double sum. So I can look at it as pi n integrating a function which itself depends on pi n, which is the sum of a j of 1 over, it's sum over I of 1 over lambda I minus lambda j f prime at lambda I. So this just means the function pi n star this the function 1 over x times f prime. So that's what it's here. Pi n at time t. So it's pi n at time t, integrating the function pi n at time t star phi. This is a function. I multiply this function by the function f prime, and I integrate for pi. Then I have the term with the Laplacian. So then here I should put Laplacian of phi. But Laplacian of phi is nothing but n times the sum of, because when I do two derivatives with respect to lambda I, in this sum only the term f of lambda I will survive, so I will have the sum of all the I. So this sum is in the Laplacian, because this Laplacian is a Laplacian in the n variables. So each of the second derivative in lambda I of phi will be n second derivative of f in lambda I. So the Laplacian of phi will be simply n f second of lambda I. So here I can write it again as, but there was, however, in the formula there was 2 over n, the Laplacian, because if you remember when we built the martingale, there was the constant c here that for us was 2 over n, and here I should add 1/2 Laplacian, so I will add here 1 over n once I factor out the n square to make the pi. 1 over n pi n of f second. Okay. And then I have to remove 1/2 the quadratic variation. So it's again the integral in dt. So the quadratic variation here should be just the integral between 0 and t of the gradient of phi squared in ds dt. The gradient of phi component I is nothing but, from the formula again, n times f prime of lambda I. So when I do the square, I have to sum over all the I, f prime square times n times n squared as well. And the quadratic variation, there was the constant c, so there is a 2 over n. And pi n, so then there is the sum of the fi square, so there is an n coming for the fact that pi n is divided by 1 over n, pi n of f prime square. T. Pi n t. So if we put all together here, okay. Maybe it's not worth, or maybe it is worth. And the martingale at time t is nothing but the exponential of pi n at time t on ft minus pi n squared times, so the exponential of n squared, and then there is pi n t on ft minus pi n0 on f0 minus the integral between minus n squared, the integral between 0 and t and dt, and here we will have pi t of dtf plus pi t of pi t star, the function 1 over x f prime, the derivative of f. Here there is a minus, plus 2 goes away with the 2, there is an n square, it's just on the quadratic variation term, it's just n square survives, so it's pi t of f prime squared without any half, minus plus, yes, 1 over n. Okay, this counts for nothing because there is a 1 over n, but let's write it in any case. 1 over n pi n t of f second. Okay, that's our big martingale. And from the inequality we just had, we have that the probability of pi n being in any set is no bigger than the supremum over all the lambda such that pi n is in A of all this expression here, which is some function of pi n. Let's call it this function let's call it L of pi n, because I have too many. So L of pi n is the exponential of n squared, blah, 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 blah. You see that there is no, like, these things depends through lambda, depends of lambda only through pi n. That's an important feature of this computation. Okay, this inequality is just this. This is 1 over et phi of lambda, but it depends on lambda only through pi n. It's some function of pi n of lambda. Okay. So this is no bigger than the supremum over all the probability measure, the curves of probability measure mu in this measurable set A of the same function of mu. Because if I optimize, if I do the supremum over all the lambda such that pi n of lambda is in A of some function of pi n of lambda, this will be no bigger than the supremum over any measure, can be any element of A of the same functional of mu. Okay, so these are, here is the supremum is just taken on all the mu's that can be obtained as some pi n, and here I'm just taking it over all the mu's in A. So, so this is nothing but so let's take the logarithm. So when I do 1 over n squared, the logarithm of the probability that pi n is in A, the logarithm kills the exponential, 1 over n squared kills the n squared, and I just get that this is no bigger than, this was 1 over this, so there is a minus because this is exponential of n squared. So this is the supremum over all the mu in A of minus, and I should copy all these things, okay? Mu t of ft minus mu 0 of f0 minus the integral between z and t, and I rewrite exactly the same thing with mu. This n square wasn't factor in anything. The integral between 0 and t, okay, of mu in dt, of mu t of dtf plus mu t star the function 1 over x plus mu t of f prime square plus 1 over n mu t of the Laplacian of f. Okay, that's our inequality. And we know this for any smooth function f of t and lambda. Any function f from time times r to r. Okay? Now, since I'm taking, so I'm doing this for any function which is, say, continuous and bounded with two bounded derivatives from 0t times r on 0t times r. So now I have to take the limit in n. Okay, I'll take the lim sup to be the lim sup over n of 1 over n squared, the logarithm of the probability that pi n is in A. Okay. This is equal to, this is no bigger than, sorry. So the supremum minus, right, as minus the infimum over all the mu in A. And there is the same expression just when I take the lean soup, 1 over n mu t of the Laplacian of f. This is no bigger than 1 over n, the infinity norm of the second derivative of f. And so it was f second. This square just one dimension. I always wrote f second, sorry. So this 1 over n is forgotten, and here I get all these, only this part. So let's give a name. Let's call this kf or if of mu. Okay, so we know this for every f continuous and bounded. Now, what we would like to do is that, okay, this is less than minus this. Since I know it for every f, I can take the infimum over all the f, and I can take the supremum over all the f in here. Now, there is a general fact, and this the following. I will not prove, but it's just a consequence of additivity of measures. For each compact set, there exists so the fact is that it's the largest that that the largest one exists, okay? There exists the largest lower semi-continuous function I from, okay, the space where your probability measures are. So these are random, pi n was a random object in here with values in 0 infinity. Such that, okay, here we took this n square. I could have taken any divergent sequence, any sequence going to infinity, but I took n square. So the lean soup over n of 1 over n squared the logarithm of the probability that pi n is in k. So this is just the law of pi n, the measure k of the law of pi n. Okay. There is a largest one for which this is no bigger than the infimum over all the mu in k of I of mu. So what I mean is just that if you take a sequence of probability measures, here the sequence of probability measure is the law of pi n. Okay, so it's the composition of pi n with the inverse, with the composition of p with the inverse of pi n. Okay, and you take here I took it in the wrong way because this statement is easy, but there is a slightly, so there exists the largest one, lowest one function such that for each compact set, for each compact set is at the end of the statement, for each k compact, okay, and so it tells us that you see this I of mu is like what I before would I write as probability that pi n is close to some mu is like e to the minus n square I of mu. Okay, so it is just a general consequence of additivity of probability measures that sigma additivity that when I take the limit of a divergent sequence, if I want to estimate the limit of 1 over something goes to infinity, the log of probability of a compact set, for all compact set is always right. There is an optimal lower semi-continuous function I for which this writes as the infimum, so for which the optimal bound writes as the infimum over all the mu in the compact set of I of mu. Namely, suppose that you have, so there is an optimal I with the following properties. Suppose that you have a lowest semi-continuous J for which this holds for every compact set. Then this J is smaller than this I. Okay? And the optimal I is just actually is what we wrote before, is the limit, so we can write it. Who is I of mu? I of mu. I of mu is trivially nothing but the limit when delta goes to 0, the lim sup when n goes to infinity, of 1 over n squared, the logarithm of the probability that pi n is in a small ball around mu. Okay. So this guy is the largest one you can have. It's the largest lower semi-continuous function that you can put on the right-hand side of this inequality for every compact set K. So, in particular, here, so how can we interpret this bound which is here? Okay, we can interpret this bound which is here as IF of mu for every f which has to bound the derivative from 0 t times r. We have that IF of mu is no bigger than, okay, sorry, I should remark that IF of mu is lower semi-continuous in our topology. This is simple because it's all linear functions. They are all integrals of mu, except this, which is a double integral. But it's again, if you let me assume that phi was, so 1 over x is a smooth function. This is just the integral, so this is just, so okay, let me first write this, because IF of mu is lower, let's write that it's continuous. Okay, in particular lower semi-continuous. Why? Because, so, who is IF of mu was this thing in blue, okay, for each given f, we have this function of mu. Topology of mu was the strong in time, but from the point of, so mu was a curve of probability measures on R. On probability measures, there were like integrals of functions, were continuous functions. So here we have integral of smooth functions, integral of smooth functions, integral in time, very well, topology in time was even strong, of mu t of some function, of some smooth function, mu t of some smooth function. The only like complicated part, it's not really complicated, is mu t of mu t star 1 over x. But this again, if you let me for a moment think that 1 over x is a smooth function, so the map that mu associates the function mu t star phi, it's actually continuous. And then I just compose mu t with this continuous function. I integrated this continuous function. So what I mean is that if mu n, say, let's think with sequences, it goes to mu, then mu t star n, and if phi would be a smooth function, mu t star 1 over x is going to mu t star, so so if mu n is going to mu in our topology of probability measure on R, then this convolution is going to the convolution uniformly, at least uniformly on compact sets. And so this is also, and so this is just, and so mu n, we know that mu n converges to mu, it means that integrals of continuous functions, so bounded functions converge. So also this is converging to the same limit. Okay. So all these things, if phi would be a smooth function, all these IF of mu would be a continuous function of mu. Now it's true that 1 over x is not a smooth function, but we should just prove that with a very large probability we can replace it with a smooth approximation of 1 over x, which one could actually prove, but we do not. So each of these, for each f, I f of mu is a lower semi-continuous function, and which satisfies this inequality. So it's smaller than the best function that satisfies this inequality. So we have this. And now the supremum of a continuous function is lower semi-continuous. So, okay, actually we don't even need this fact. I continue in here, in any case I remember who is I mu of f. So if you want, we have that I of mu, I can optimize, is no smaller than, actually then we should prove the other bound because it's really equal, is the supremum over all the function phi that are smooth, let's just write smooth, so two bounded derivatives, of IF of mu. So on compact sets, or if I take small balls and then the limit when the ball is small, in any of these two cases, we get that. Okay, using this general effect. I don't prove this general effect because this is a sort of a topological nonsense. I mean, you just write that you can cover a compact set with finitely many balls. On each ball, you minimize your function and so on. There is nothing specific of this problem. It's just a very generic. It's a fact that holds for any sequence of probability measures. Just if you don't take here, we took here 1 over n squared and got some bound. If you take here, I don't know, 1 over n, you will get some bound, which is always 0. So there is always such an optimal functional. Of course, if you choose the wrong speed on which you divide the log, you will get some trivial function like 0 or infinity. Here we got something non-trivial, which tells us that we sort of catch the right speed of convergence, exponential convergence of this probability. So, okay, so we have that for each k compact or we have this inequality with this. So in some sense, we are saying that if we know this for every compact set, then we can exchange the supremum with the infimum in this inequality. So, okay, or we can write like this because that's how we stated the theorem. It's actually equivalent. The limit when delta goes to 0 of the lin sup of the probability of 1 over lin sup in n of 1 over n squared. That's how we stated the theorem of the logarithm of the probability that pi n is in a small ball around mu, and delta is going to 0 after the limit in n. So this is what we call I of mu, and it's so this is what we called minus I of mu. Sorry, otherwise this would be. Sorry, there is a minus in the first formula. Otherwise, I is positive, and that's the log of a probability. So this is what we call the minus I of mu. And so it's less or equal because I is bigger than the supremum, that minus the supremum over f of IF of mu. Okay? So who is IF of mu? This supremum. Look. So let's make a very simple remark first. Okay? Remark. So if H is an Hilbert space, I can define a norm on the dual of this Hilbert space, so on the space of continuous linear function on H. The dual norm, what is the dual norm? I mean, it's not that I can define. The dual norm, okay, I can define it just as the supremum over all the x in H with the norm H equal to 1 of y of x, sorry. But this is just simple algebra. You just optimize over the computation with the parabol. This is, it's the same as doing the supremum over all x of y of x minus the norm of x squared. Just if I do this, there is a 4. I hope. Because like you make an identification of H and H star, and the optimal x is x equal to y over 2. So that's y squared over 2 minus y squared over 2 squared, which is 4. So to get y squared, you get this 4. Okay, it's just a simple way to write a dual norm. So here, what is IF of mu? This is the supremum over all the smooth function f of mu t of ft minus mu 0 of f0 minus this very long integral. So mu t dtf plus mu t of mu t star f prime minus mu t star phi f prime minus mu t of f prime squared. Okay. Now, what is all this? The first part, not the mu t of phi prime squared, but this, like, if you think for a moment that mu t is like a function of t and x, this would be just So the first thing, yes, is just like when you write PDEs, it's just, or ODEs, it's just the weak version of integral between 0 and t of dt mu times f. Okay. So let's write it informally. If mu t, if we think that mu t is like a smooth function, if of mu is like the integral between 0 and t. So this is just the boundary term of the derivative integration by parts. So this is just of in dt of dt mu t times f plus, and this again, there is f prime. I can integrate by parts this f prime. So this should just be like dx of mu t star 1 over x times f. Okay. And then there is minus the integral between 0 and t in dt of mu t of f prime squared. Okay. So it's just like integral between 0 and t of dt mu plus dx. Oh, here I forgot a mu, sorry. Of mu t star phi. Okay, f minus mu t of f prime squared. So, okay, here there is only a little problem. Here there is a derivative. Suppose that if I have to take the supremum, then I want to do the supremum over all the functions f, the supremum over all the functions f. So this is all linear in f minus something quadratic in f. Yes, it looks like this formula. Just so suppose, just to understand what it means, this supremum. So this supremum is what we will call the norm or blah 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 that was written before. Just what's the idea? The idea is that if here, for instance, there was minus mu t of s squared, yes, so that we do not get confused by this derivative, all this thing, yes, when I do the supremum, is just using the simple remark, is the supremum of something linear in x minus the norm of x squared. So here, our Hilbert space will be, if there would be no derivative, just the square, it would be the space of L2 functions, but okay, taking the supremum of a smooth function, taking the supremum of something times f minus something times s squared, taking it on L2 functions, smooth functions is the same, so it would be really that formula where the norm of x is the norm of f is the L2 norm. If here there wouldn't be f prime squared. This means that this supremum would be nothing but dt mu plus dx of mu t star phi norm L2 of mu squared. Okay, 4 times. 1/4. Yeah, 1/4. So the supremum is 1/4. Now there is, but it's not the case because it's f prime, it's not f. So again, if you think that this was like the derivative in x of something, then we would get the L2 norm of this something because you integrate this derivative by parts on f. So that's exactly what is so like this. So this all this supremum is what we call. Sorry for the too much blue chalk. This supremum is what. So let's do this. We define the h minus 1 with weight mu norm square as the supremum of the integral between 0 and t in dt of, let's call this, I don't know, v, of v of t and dx times f supremum over all the f minus integral in d mu t of f prime squared. Okay? So this is our definition of this h minus 1 mu norm, where mu is the measure which is here. Okay? So our functional supremum over f of I of mu, of IF of mu, supremum over f of IF of mu, with this definition is just 1/4 the norm that depends on the same mu which is here, and inside there is also something that depends on mu. Okay. So that's how we interpret. So the fact that we write this norm like this is just the definition of. Is just that we are defining the norm as the supremum of IF of mu. That's all. That's why we call it a norm. Just as nice that we can interpret it as an Hilbert norm, because just by this simple remark, okay, it was something linear minus something, the supremum over x of something linear in x minus something quadratic in x. So that's why it's certainly, not L2, sorry, h minus 1 with weight mu, okay? So if there would be no derivative in f, that would just be an L2 norm. Since there is a derivative in f, it's the dual of a Sobolev space, yes, of a space where there is an L2 norm of the derivative of f, and it's weighted with the measure mu. So that's why I call it h minus 1 with weight mu. So if you want to use current notation, this is called just a weighted Sobolev space. But in reality, it means just this supremum, nothing more, nothing less. Okay, even because mu is, never forget that mu is a measure, so it's not really a function. So, like this writing is a bit informal. One could prove in this case that it's really that is absolutely continuous with respect to Lebesgue, but it's if this supremum is finite, but it's. We don't need to use it. That's just this supremum of f of IF of mu, by definition, we call it this norm because it can be interpreted as an Hilbert norm. Then it's nice to write it in this way because we understand that it's sort of because it's sort of how much this equation is not true in some sense. How much the equation dt mu minus dx of mu star phi is violated, but. So it's just an interpretation. Then this norm means nothing more, nothing less than that supremum. Okay. Okay, this we got for pi n. So what we proved one inequality in some sense. So the statement was that pi n, the probability that pi n was close to mu goes like the exponential of minus n this function of n squared, this function of mu. In the sense that if 1 over n squared the logarithm and the limit in n and the limit when a ball goes to the radius of the ball goes to 0, I get exactly minus I of mu on the right hand side. So that's what this means. We proved that this limit is no bigger than. Also the other inequality is also true. But say for us it's this one is somehow more interesting, this inequality. And then how do we use it if we try to predict the behavior of the largest eigenvalue of our matrix? So the largest eigenvalue will satisfy this equation. W dot 1. Yes, where this is a Brownian motion. And so I can write this as pi n star. So these all are at time t, no? So this is pi n at time t star function 1 over x in point lambda 1 plus square root of 2 over n w dot 1. And now the claim is that lambda 1 also satisfies a bound of this type, but with e to the minus n, not with e to the minus n squared. What is the idea? The idea is that I have n eigenvalues. Each of them have a noise of size square root of 2 over n. So since in the noise you should always look at the square, you should always look at the quadratic variation, sort of having a noise here which matters, because if I just take the limit n goes to infinity, this noise didn't matter. What is the probability that this noise, in some sense, matter? Is e to the minus n times something, okay? But order e to the minus n. So if I want, in some sense, how improbable is that the first eigenvalues moves? Is improbable as e to the minus n. The second eigenvalues moves is improbable as e to the minus n, and so on. But if I want to move all of them, of course, they are dependent, but the order of the probability will be like as if they would be independent. So if I want to move n things, each of them has a probability to the minus n to be moved by a noise, I will get e to the minus n squared. Okay, it's like e to the minus n to the n. So this is very useful in here, because now if we interpret the equation in this way, yes, and we have these ideas of this will change, the probability this changes its order e to the, so if I just to look at events of probability as small as e to the minus n, pi n t, okay, it will be basically already the semicircle law, because the probability that pi n is not in the neighborhood of the semicircle law is as small as e to the minus n squared, and then just looking at events of probability as small as t is to the minus n. So in this formula, fluctuations of pi n will play no role. Even if I look at the very sharp asymptotic of lambda 1, or say the sharp asymptotic of lambda 1, the fluctuations of pi n will play no role. And only the fluctuations of this Brownian motion will play a role. So of course we can write this quite precisely, but that's the idea. So it is like in any case, when I will reason on this equation, I can think that pi n is already the semicircle law, because I will just all probabilities will intersect with the probability that pi n is not in a neighborhood delta of the semicircle law, and this probability will be extremely small. So here we'll do the same. As I did before. So here I want to prove a second theorem, which is the following. So the probability, so for each, let's be slightly informal, for each x, deterministic, for each function x from 0t to r, for each curve, let's say at least continuous. In reality, we will mean infinity, so C0t with values in R, if x is not smooth enough for each x. The probability that lambda 1 is close to x, so, okay, I will write again in what sense. This goes as exponential to the minus n, and here we'll have, so x dot minus, so here it's I did the computation. I wrote it exactly because I don't remember. So it will be just the integral of 1 over x for the semicircle law scaled with time t. Okay, it's here over so xt minus 1 over 2t. X minus xt minus square root of x squared minus 4t. So this is L2 norm square. So this is just L2 in time. 2 of 0t. So we should be a bit precise here. This means, because there is a square root of something that a priori may be negative, but it will not be. So this means that the limit when delta goes to 0, the limit when n goes to infinity of 1 over n, the logarithm of the probability that lambda 1 is in the neighborhood of t of x. So this means that the supremum of a t less than t, that lambda 1 of t minus x of t is less than delta. Okay, this probability, this limit is equal to minus. Okay, and here we mean the integral between 0 and t of x dot t minus 1 over 2t xt minus the square root of xt squared minus 4t squared in the t. If x is actually, I can do, if x is absolutely continuous, so I can make a derivative almost everywhere, and however also xt, so here, is always bigger or equal than the 2 square root of t. But that's clear, that's the largest eigenvalue, and we already know that the empirical measure converts to the semicircle law with radius square root of t. So the largest eigenvalue cannot be small. I have kind of, in any neighborhood of 2 square root of t, I have a positive fraction of the n eigenvalues. So certainly the largest one cannot be smaller than 2 square root of t, and plus infinity, this means plus infinity otherwise. So again, let's just prove the less or equal, which will tell us that xt is actually, that lambda 1 of, in particular, with the less or equal, we will know that if you solve this equation equal to 0, we will know that lambda 1 of t will converge when n goes to infinity. So here lambda 1, never forget that lambda 1 of course depends on n. When n goes to infinity, lambda 1 will approach with probability, say, which is exponential, so with the probability that this doesn't happen is exponentially small in n. So lambda 1 will approach at every time t, even continuously in t, the boundary of the semicircle law, of the support, sorry, the boundary of the support of the semicircle law. So in particular, will converge to 2 square root of t. So the probability that it doesn't is exponentially small in t. Exponentially small in n, sorry. I can erase this. So we reason exactly, let me be quick on this, because the proof, like the technique of the proof is exactly the same as we did before, but instead of building this very large martingale, lambda 1 is just one-dimensional, so we can build just a one-dimensional martingale. And let's say the following. Just let's call say a delta, the event where the supremum of a t of delta pi t n star phi at lambda 1 minus pi t star phi minus, sorry, so okay, sigma t star phi at lambda 1 is more than delta. So where sigma t is, I wrote at the beginning, is the semicircle scaled at time t, so it's 4t minus x squared, is the measure dx, 4t minus x squared over 2 pi t. And that's where this function comes from. Sigma t star phi at x is equal, for x bigger than square root of t, 2 square root of t. This integral, okay, you can do it. I did it, and this one is the one is the result I just copied from my notebook, 1 over 2t, x minus the square root of x squared minus 4t. This is just a one-dimensional integral. Okay, you can do through Residuus theorem. Very well. The theorem of residual. So that's I delta, and from the previous, if we pretend for a moment again that phi is more or less smooth, we have that the probability that of A delta, okay, this is, you see, this is less, okay, it's bounded by e to the minus n square C delta, where C delta is strictly positive for every delta, okay? What is C delta? C delta is the infimum of I of mu over all the mu such that mu star, mu t star phi minus sigma t star phi is more than delta. Okay. I of mu, okay, this is basically a almost continuous function of mu, and I of mu was 0 only when mu t was sigma t. So the probability that this happens is like the probability that you are far enough from sigma t, and this was exponentially small as e to the minus n squared. So when we do now the same trick with the martingale as before, we had the probability that, say, lambda 1 is in some set, okay? Well, I can make a martingale, let's call it again Et phi, which now will be just e to the phi of t, and lambda 1 at the final time t minus phi of 0, and lambda 1 at time 0 minus the integral between 0 and t of pi n t star phi on lambda 1 of t, phi prime of t and lambda 1 t, minus 1/2 plus 1/2 second derivative in lambda of phi of lambda 1 alone. So I'm writing again the exponential martingale, but for the one-dimensional process lambda 1. So I'm doing fast because it's exactly the same technique we used for pi n, just the. So this is a martingale for every phi. I continue the exponential in the next line. So minus the integral between 0 and t of 1/2 the phi second of t and lambda t, and then there is the lambda 1 t, and then there is the quadratic variation here, which is just 1/n, the integral of phi prime squared of t lambda 1 of t in dt. So this is between 0 and t. This is p dt phi in t and lambda 1 of t plus. Okay, there are all these terms. It's the same as before, except for, oh, I mean, not the same as before, but it's like the same type of martingale. And now, however, the eta term, it counts here. And it's not like before that it was 1/n. It counts in here. And so we want to get that this scales well with n. So we choose phi as n times a certain phi of t and dx, or say phi of t and dx, as n times some arbitrary function f of t and dx. Before, you remember, we had n variables, and we choose it as n times the sum of some given function in t and lambda I. So if we do this, why we choose this n here, so that n will come here, n will come here, n will come anywhere. And for phi prime square, we will have n square that will kill with the 1/n. So all these terms will be exactly of the same order. And then reasoning as before, we have that the probability that lambda 1 is in A is equal to the probability that lambda 1 is in A times this martingale divided by the same martingale. And okay, before we took out this supremum, the 1 over the martingale with the supremum, and I think we read say now that this is less or equal than the probability that lambda 1 is in A times the lambda 1 is in A intersection with the set A delta. So this was supposed to be a calligraphic A delta. And then there is ET divided by ET. Plus the probability of A delta. Okay. So I would like here, now on A delta, I can basically replace for free up to paying a small delta this PTN star phi with sigma T star phi. So this then, once we do this, this side will work exactly like before, while this is very small. So just let's make a simple remark before we go on. If I do the limit when n goes to infinity of 1 over n, the logarithm of an plus bn, so where an and bn are some positive numbers, sequences, this is equal to the maximum, okay, maybe the lim sup, say, to the maximum of the lim sup of 1 over n, the logarithm of an, and the lim sup of 1 over n, the logarithm of bn. Why is this true? Because, well, certainly the left-hand side, these are positive, so the left-hand side is smaller than this and smaller than this, so it's smaller than the maximum, but is of course bigger than, it's bigger than the maximum. It's bigger than this, and it's bigger than this, so it's bigger than the maximum. But at the same time, it's smaller than, so an plus bn is smaller than twice the maximum between an and bn. But when I take the logarithm of twice the maximum, this is the log 2 times the log of the maximum, and 1 over n kills the log 2. So in the limit, they're just the same. So here, when I will take 1 over, so this implies that when I do the lim sup of 1 over n, the logarithm of the probability that lambda 1 is in A, intersection with A delta. Okay, then this martingale I should have added later, plus the second probability, an delta, A delta here, okay. I do the logarithm of this, so this is our an, this is our bn. But bn is smaller than e to the minus n squared, something positive. So when I take the lim sup, this is just minus infinity. Okay? So this limit, okay, is the maximum between the limit of the first guy and minus infinity. So I can just forget the second. This lim sup is equal to the lim sup of 1 over n, the logarithm of the probability intersection without this, okay? So when I will take the limit in this series of inequalities, I can forget an, because in the limit, because the 1 over n log of this goes to minus infinity, and in the maximum it will never count. So, very well. So we have this, less or equal, less or equal. So I continue from here. Reasoning exactly as before. This is now less or equal than. Let's be okay. I should take the infimum of e of 1, the supremum. So here I have the supremum. That's what I should do, right? 1 over E and F T. Okay. And here I should take over all the elements in our probability space, say the lambdas, all the lambdas, such that lambda 1 is in A, and say lambda, the family, lambda 1, lambda 2, lambda n, is such that A delta holds. Okay. if you want A delta, I erase the name. It's just the set of all the continuous functions lambda from 0 t to Rn, such that this holds. Okay. So, okay. And now this is what? This is, okay, up to a small error delta, this is, say, okay, this is no bigger than exponential to the minus. So here I wrote less or equal. In reality, this means when I take the logarithm, right? But okay. E minus, okay, what is written there? Phi of t, lambda 1 of t, minus phi of 0, lambda 1 of 0, minus, then there is the integral of dt phi in t lambda t. And here, up to paying a price delta t, I can replace pt star phi with sigma t star phi. This phi. The function 1 over x times phi prime of t lambda t. Yeah, it's less or equal, so if I add, okay, I just add e to the delta t to change pnt star 1 over x with sigma t star 1 over x minus 1/2 phi second of t and lambda t minus the integral. Oh, this I called f, sorry. Phi was an f, sorry. Everywhere there is phi, I put f, I'm really sorry. F second, f, minus 1/2 f prime of t and lambda t squared in dt. Okay. Then, as before, we take, okay, I will do even more now. Once I do this, if I remove the restriction, the lambdas in a delta, once I replace it with, I pay this delta, I mean, it's still an inequality if I remove this supremum. And when I will take then the lim sup, when n goes to infinity, of 1 over n, the probability that the function lambda 1 of t is an arbitrary measurable set A, this will be no bigger than, I forgot here, the n's, okay, phi, which was in this martingale, was n times f, so there is an f everywhere, and here where it was phi prime square, it was divided by n, so it's still just, is n squared divided by n, it's still just an n. I have these now for every delta, I can optimize over delta, and this will just die, to get minus f of t and lambda 1 of t, minus f of 0 and lambda 1 of 0, minus, sorry, this is minus, sorry. So like before, this, what is here is a function of lambda 1. All the other lambdas have disappeared. So when I do the supremum of all the lambda 1 in A, of something that only depends on lambda 1, I can write it as, okay, then the supremum is no bigger than the same supremum of all the x in A, arbitrary elements in A, so 1 over n, logarithm 1 over n kills the exponential to the n. So it's delta t minus, and then there is f of t and x of t minus f of 0 and x of 0 minus the integral between 0 and t of dtf plus sigma t star phi times f prime plus 1/2, inside the integral is plus 1/2 f second 1/2 f second minus f prime square, all computed in t and lambda and x of t in dt. Okay, this is true for every delta. So I can kill now delta. And there was delta minus, so the minus still stays. And this is equal to minus the infimum over all the x in A of the same thing. And the reasoning as before, here I can say it's minus the infimum. So this probability, this leading super probability is less than minus the infimum over all the x in A. And now if I restrict to the A compact or I do the limit on small balls, I can exchange, since I know it on all compact sets, I can exchange, I can optimize over all the f, so take the infimum over f. Infimum with the minus will become a sup, but again, the important is that if I know it on all compact set, reasoning as before, I can exchange the supremum over all the f with the infimum over all the x with the infimum of the supremum, because in our topology, which is now just C of 0t, this is certainly a continuous function. For each f, this is certainly a continuous function of x. So I can exchange here this inf minus inf with minus inf sup. So this will be like before, infimum over all the x in k of the supremum over all the f of this. And now, okay, doing this supremum over f, this q sigma t star phi is the function I wrote before. It's 1 over 2t xt minus the square root of xt square minus 4t. That xt should be bigger than 2 square root of t is actually a consequence of the semicircle law, because it's the largest eigenvalue and it's a continuous function of t. And then you can easily compute this supremum. In reality, is enough to take, when you make this supremum, so the supremum over f will not be smaller than when you take the supremum. It's enough to just make this an arbitrary function of t times lambda. That's how I say f of t and x. It's actually enough to make the supremum of a linear functions in this. So it's actually a sign a bit of, I wouldn't say triviality, but say the fact that it's enough to take linear functions in here. So when you make this supremum, or in any case you can enjoy your, if you just take linear functions, you see that here there is arbitrary function of, so yeah. Yeah, let's do it. In any case, it will be enough to take a linear function of x to check that this supremum is nothing but the functional I wrote, or in any case, say no bigger, it's enough for us. The function I wrote at the beginning, which is the L2 norm of x dot minus sigma t star. So 1 over 2t xt minus the square root of xt square minus 40. Usual L2 norm in time squared. So we just reasoned as before. So I have to do the supremum over all the f. Certainly is no smaller than if I take just linear functions. F of t and x is alpha of t, arbitrary function of t, alpha of t times x, which will give me, so if we call all these now, we call it jf of x. Okay. So the supremum over all f of jf of the continuous function of time x. This is certainly no bigger than the supremum over all the functions just of time. And then I plug in the function of t and x, alpha of t x. So this is alpha of t x of t, x, yes, alpha of t. Alpha of t x of t minus alpha of 0 x of 0 minus the integral between 0 and t of dt alpha time x of t dt. then there is then there is the integral between 0 and t of sigma t star function 1 over x in xt times f prime, so it's just alpha of t because f prime is the derivative in x. The second derivative in x is 0, and it remains minus the integral between 0 and final time t of f prime square. So that's just alpha of t square in dt. But it's the same, well, not really the same, but we can reason again as for the spectral measure pi n. This is nothing but the weak version of the integral of dtx, so let's call it x dot t alpha of t, x dot of t alpha of t dt. Yes, it's just by integration by parts. What I mean that if x is absolutely continuous, that's actually true. If x is not absolutely continuous, you can really easily check that the supremum over all the alpha of these minus alpha square will be plus infinity. So, so otherwise you can just write it at x dot times alpha of t, and then this is just, so it's again, it's like before, it's the supremum of x dot of t alpha of t minus, again, some function of t, sigma star phi alpha xt, something times alpha of t, so still linear in t, minus something quadratic in alpha, which is just the L2 norm. So it's the so this is equal to 1/4 the dual of the L2 norm of the things that multiply the linear part in alpha. So the dual of the L2 norm is just an L2 norm. So it's x dot minus sigma t star phi at x, so this depends on sigma t star phi in xt squared in dt. So that's it. I was a bit informal, but I hope the general idea was more or less clear what it was. So we start with this matrix of random processes, made a random diagonalization and found out that the n eigenvalues satisfy sort of mean field equation, like n particles on the line that interact with each other with a two-body interaction. And using this fact, we have checked the first that the spectral measure of this matrix not only converges to the semicircle law, but the probability that is in some sense away from the semicircle law is exponentially small as e to the minus n squared. And we computed a very sharp bound, which is actually, we made it less or equal, but in the limit is actually also bigger or equal, with the sort of differential characterization of how much pt is not the semicircle law. Pi t is yes. So in this, if you remember, there was just a very precise differential function with the h minus 1 norm, but but okay. And then we use the fact that pi tn has this very, very small fluctuations, e to the minus n squared, to compute the sharp asymptotic of the largest eigenvalue of this matrix, which also satisfies, so maybe I can finally write this formula. I mean, the one that was declared in the theorem, it was that, so the probability that the largest eigenvalue is close to a given path x, this goes as e to the minus n, 1/4 the integral between 0 and t of the derivative minus 1 over 2t xt minus the square root. So it was. So we have a very precise formula, which is not so. So it's xt squared minus 4t L2 norm squared, and this means actually infinity if the path xt is not absolutely continuous or is not bigger, or or it's not bigger than 2 square root of t. Okay, just using the fact that in some sense in the limit when n goes to infinity, the interaction with all the other eigenvalues averages, and it gives a very, very small contribution, actually negligible contribution to the fluctuations of the first eigenvalue, and only this Brownian component remains. Okay, so probably this last lecture was a bit hard, but if you want to be like, I hope I could give at least a bit the idea. It's not equal, it goes like. And of course, if you want more details, you are welcome to contact me or to ask for references. Okay, that's all.